Welcome, and for this final lecture for this series on curves over finite fields. So one last thing that we have to speak about is going to be a bit more technical than the rest of the course, because we will have to speak about Jacobians of curves, and especially so Jacobians over finite fields. So, as usual, we start with the curve C. It's going to be mostly over FQ, or let's say I don't fix FQ, so I fix a field K, so a curve of genus, and I'm going to exclude directly genus 0, which is not going to be very interesting for studying the Jacobians. And all I'm going to say, or most of what I'm going to say, correspond to some chosen part, chapter 7 of the notes. Let me first remind you of an object that we have already seen in the context of divisors of curve, which was what we denoted peak 0 ck, and that was exactly the divisors of degree 0 on C defined over k up to linear equivalence. And remember that the divisor of degree 0, well, the degree 0 is easy, but a divisor, a rational k divisor of degree 0, doesn't mean that each of the points that are in the support of the divisor are rational, but that the divisor is gal of k bar over k, Galois invariant. Okay? Also, I mean, the notation that we are using here seems to indicate that we should be able to consider this set as the set of k rational points on an object. And this is exactly this. I mean, right now we have just a group, but this group comes from a variety, an algebraic variety, and this is going to be the Jacobian. Except that in general it's a bit more technical, so here is a definition theorem. So there will be a lot of completed words, but don't worry, I mean, we are going to explain them. So there exists a principally polarized abelian variety over K of dimension G, and that's why I wanted to exclude G equals 0, because then it would be just a point, such that, so-called the Jacobian of C, and denoted Jac C, so such that if I look at the k rational point on Jac C, these are the k bar rational point, or the k bar elements of peak 0 C, which are invariant by the action of gal of k bar over k. And if, or let's say here, and Jac C over any extension k prime, so k prime is going to be just an extension of k, is going to be exactly the element of peak 0 defined over k prime as soon as C key prime is non-empty, or more generally, as soon as there exists a degree 1 divisor, or degree 1 rational divisor on C. Okay. So, and that's why, I mean, remember in the last lecture, I insisted a bit on the fact that because of Haswell bound, when Q was big enough in comparison to the genus, one has always a point, a rational point on a curve. So over FQ, I mean, this condition to have a point is mostly satisfied all the time, but it's even better. We will see that actually it is always satisfied if we go to the condition where we ask for degree 1 non-trivial divisor on C. And well, let's say, I mean, I can say it already now, so this condition, so remark, over FQ by the proof of in 6.1.1, where we prove that something which was called delta 0 is equal to 1. This implies that there exists a degree 1 rational divisor for any C over a finite field. So over finite field, the situation is particularly nice, as we have always equality. We don't have to take this gal of k bar over k. And we can somehow, as long as we speak about points, I mean, we can identify the point on the Jacobian and the element of the peak 0. So this is quite nice. But in general, I mean, it might be not the case. So still as a remark, in general, so peak 0 ck can be smaller than Jack ck. And I'm going to give you an example. So consider E defined by y squared equal minus x4 minus 1. So this is a genus 1 curve, at least when you take its non-singular model. And let now x0 be a solution of x0 to the fourth is minus 1. And P1, the point x0, 0. P2, the point minus x0, 0. P3, the point I x0, 0. And P4, the point minus I x0, 0. And I should say that this elliptic curve, I took it over the rational. And I'm going to define D, the divisor, which is P1 plus P2 minus P3 plus P4. So it's a degree 0 divisor. And one can easily see that if I take sigma, the element of gal of q bar over q, which ends x to ix, what is this sigma? So this becomes ix0, so it becomes P3, this becomes P4, and P3 and P4 becomes P2 and P1. So this is actually minus D. So it is not stable. So it is, so this implies that D doesn't belong to peak 0 E over Q. However, now what I can see also is that so D sigma, which is minus D, is linearly equivalent to D, because if I take 2D, 2D is going to be the divisor of the function x squared plus or minus, so minus x0 squared, x squared plus x0 squared. So because of this, then, D belongs to Jack C of k. Okay, because the gal action here is on all peak 0, so it's up to equivalence only that you want an equality, not an equality as divisor, but an equality as classes of divisor when you apply the Galois action. Okay, but as we said, I mean, over finite fields, we are quite happy. We won't have to deal with this kind of problem. Okay, what about the words in the definition theorem? There are plenty of them. They are like something which is called an abelian variety of dimension G. So we are going out of the world of curves to algebraic variety of large dimensions. There is the world of principally polarized, which is also a bit complicated. But luckily, if you have followed, or if you are going to follow the lectures of Anna, you will see that in the case of complex field, you can get quite a very nice intuition about all these objects. So Anna has a series of lectures, so let me think if I have, yeah, so to understand abelian variety and their polarization over C, look at Anna's Somoza lectures, part 3-4, and for part 5-6 for the complex understanding of how to represent the Jacobian of the curve. And you will see that there is still another way to see this peak zero of C as a certain torus. Okay, so this is nice, and somehow it is sufficient for getting the intuition. Of course, if you want to really understand abelian varieties and the polarization over any field, having a complex version is not enough. So you will need to study more, and there are references in the text that I wrote where you can see much more about abelian varieties. But I will try to stick with globalist intuition because mostly we are going to play with formal properties of these abelian varieties, and we don't need at first approximation to really understand what the words mean in a precise context. So how to play effectively with the Jacobian of a curve? First, I mean, when you have an elliptic curve, then the Jacobian of E is the same as E. And then, I mean, you have already seen also in one of the first lectures of Anna that there is a group law on the elliptic curve. So adding points inside the Jacobian of E is the same as adding points on E, and we know how to do it. In general, so if now C is of genus greater than 1, there are algorithms to play with the points on the Jacobian. It depends a bit. I mean, there are two flavors. There is one which is usually based on looking at the curve as a certain function field over a finite field, or over any kind of field. I mean, it works as well. I mean, this has been developed quite thoroughly in Magma by Florian Hess. And there is also another way, more geometric, to look at the Jacobian, which also has been developed by Kamal Khoury-Makdisi. And these two approaches, they give more or less the same complexity as asymptotically to try to work with these curves. And so, I mean, this is something which is doable. What I would like to show you is just a principle on how this is done. So everything is based first on the fact that you need to represent the element inside the Jacobian. So how are you going to represent them? And this is easy. This is the following lemma. So let D0 be a rational divisor of degree 1 on C, and we know that over finite fields it always exists. Then any any point that I'm going to denote D on the Jacobian over K is linearly equivalent. And here you see that what I'm using is already the identification between the Jacobian and the peak zero to something that I'm going to denote D plus minus G times D0, where D plus is effective. And the proof is super short. Just apply Riemann-Roch theorem. Because if you look at L of d plus g times d0, the degree is g minus the genus plus 1 plus a contribution that I don't care. This is greater or equal to 1. And the fact that it is greater or equal to 1 tells you that there is an effective divisor which is linearly equivalent to d plus g d0. So this is great. This is great because now, an effective divisor is just a sum of points. Maybe the points are not defined over the field, K itself, but at least it's a Galois stable sum of points. As a remark, this thing that we did here that is just looking point-wise can be pushed a bit further, and this would be the lemma 7.2.1 in the notes. If you look at effective divisors of degree g, the set of them, you can see them as points on a certain variety, this variety being taking the product g times of the curve. So this gives you like an order set of g element of g points on the curve, but the divisor, you kill the order. So all you have to do is actually taking the quotient of this variety, and there is a way to do this by the symmetric group. And doing this, you still get a smooth variety. And this smooth variety, actually it's not too far from being the Jacobian, meaning that it is birational to Jac of C. And birational, it just means that if you have an open set on the Jac C, you have an open set on this variety, such that if you restrict on this open set, you have an isomorphism between them. So you understand almost all point or all the geometry of the Jacobian with this quotient, but of course, then they are like codimension 1 sets for which you need to be more careful. Okay, so that's one thing. So that's how I'm going to represent my element in Jac C. Now, how am I going to add them? And for this, I'm going to give you here an example for genus 3 non-hyperelliptic curves. And if you remember one of the lectures that we had, genus 3 non-hyperelliptic curves, I can embed them canonically inside P2 as plane or smooth plane quartics. So this is how I'm going to represent them. Now, what I'm going to use is not exactly, I'm not going to describe exactly my divisors on the Jacobian as d plus minus g times d0. I'm going to cheat a bit because it's going to be easier. So it's not exactly in this framework, but I'm going to request something. So request that there is always a line cutting the quartic in 4 rational points. Okay, I do this assumption, and one can prove that this is always the case if Q is large enough, meaning greater or equal to 127. So I'm going to assume this, and you will see that it simplifies the algorithm. So now let me draw blah, blah, blah. my quartic C, and I have a line L infinity that cuts the quartic in 4 points. Okay. And because, I mean, this theorem or this lemma that I just gave over there doesn't really depend on the fact that one uses GD0. What really matters is that you have something which is of degree G. So instead of taking G times divisor of degree 1, I can directly take a divisor of degree 3 in this case. So my divisor at infinity, so D infinity, is going to be P1 infinity plus P2 infinity plus P3 infinity. So any D inside the Jacobian of C over K, I'm going to represent it as D plus, an effective divisor that I denote D plus, minus D at infinity. Okay? And now the game, I mean my input are two effective divisor of degree 3, D1 plus and D2 plus, and the output would be a divisor D plus, such that D plus minus D infinity is D1 infinity minus D infinity plus D2 infinity, D2 plus minus D infinity. Okay? So I do the addition of this divisor, and I'm going to represent it as an effective divisor of degree 3. And I say, I mean, the procedure is the following. So first, consider a cubic E passing through, maybe with multiplicity, but I write it just like this, passing through the support of D1 plus, D2 plus, and the point P1 infinity, P2 infinity, and P4 infinity. So is this possible? I mean, how many points do I have? I have 3, 3, and 3 is at 9 points. And a cubic, a plane cubic, is given by 10 projective coefficients, so you can fix arbitrary going through 9 points. So I mean, this is possible. And also because I have assumed that all my points at infinity, and of course these two divisors are rational, the cubic E is going to be defined over my field FQ. I mean, if here I'm over finite field, let's say. Okay, so I don't know if I dare doing a picture of this. I mean, it's always a bit delicate. But if I do this, then I would have a point P1, P2, P3 maybe, and then a support for the other divisor. So that would be, no, that's a bad idea. So P, Q, and R, P1, Q1, R1, and P2, Q2, R2. And then I go through the points also P1 infinity, P2 infinity, so, and P4 infinity. So something like this. Okay, so it starts like this, and of course now what? You have a curve of degree 3, a curve of degree 4. What Bézout's theorem tells you is that the number of intersections should be 3 times 4, 12. You have already 9 of them, so you're left with 3 extra points. 1, 2, 3. So these 3 extra points define a divisor that I'm going to denote P3, Q3, R3. So passing through things and defining a residual divisor. So I said P3 plus R3 plus Q3 that I call D3. Okay. D3 plus maybe. Now, second step, a conic. You define a conic Q, which is also going to be about FQ, passing through D3 plus and P1 infinity, P2 infinity. So is this possible? Yes, again, because the conic is 6 coefficients. Here I have 5 points, so I can always impose this. And so let's see if I can draw this. Usually, then that's where it goes wrong because you have selected the point a bit in an arbitrary way. So it was P1 and P2. But was I right? Okay, seems so. So P1 and P2, and these 3 things here. Maybe I can. Wow. Okay, and then I will need to have also a residual divisor. That's going to be complicated, but now let it go a bit more like this. Okay, that's right. Okay, well, it's supposed to be a conic. But anyway, so it goes through these points, and there are, of course, again, because it's 2 times 4, that's 8, and you had like 5 points, so you had a residual divisor here of degree 3. Okay, so let's denote it, I don't know. P4, Q4, R4, and defining a residual divisor P4 plus Q4 plus R4 that I denote D plus. Is that okay with respect to, yes. So now why does it work? Because you can look at your elliptic curve, as a function of degree, the quotient, of the equation of your elliptic curve by z cube, this is, you can look at it as a function on your curve. And you know that because you have the canonical embedding, it means that, the divisor of this is equivalent to 0, so the divisor of cut by the elliptic curve on the curve C, has to be linearly equivalent to 3 times the divisor cut by the line at infinity with the curve. But as it is the canonical embedding, the divisor cut by the line on the curve is the canonical divisor. So the divisor cut by the equation of E on the curve C must be 3 times the canonical divisor. And in the same way, the divisor cut by the conic Q on the curve must be 2 times the canonical divisor. So let me write it in this way. So what we have is D1 plus D2 plus P1 infinity plus P2 infinity plus P4 infinity plus D3 plus. This is equivalent to 3 times the canonical divisor. Now D3 plus P1 infinity plus P2 infinity plus D plus, this is 2, and obviously on the line at infinity, so P1 infinity plus P2 infinity plus P3 infinity plus P4 infinity, this is the canonical divisor. So now I take this identity and I do minus these two. So minus, minus. And what I get, I mean, D1 plus is going to survive, D2 plus is going to survive. This one is killed, this one is killed. P4, so let me see. The P4, yeah, which is killed here. So what is left, and these ones are also dead, so minus D plus or minus P1 infinity plus P2 infinity plus P3 infinity, but I think that was the definition of what I call the infinity, is equivalent to, well, nothing. So I can rewrite it as D1 plus minus D infinity plus D2 plus minus D infinity is equivalent to D plus minus D infinity. And this is exactly what I wanted to sum my two divisor here and here, or my 2 points on the Jacobian. Perfect. And maybe let me just leave you with one question. I mean, because you could say, why did you go out from the framework that you said? I mean, just take D0, a rational divisor of degree 1, like for instance a point maybe, if there is a point, a rational point on the curve, and take as divisor infinity G times this point. So, question for you, if P0 is a point on the curve, define D infinity as G times P0, can you find the geometric way to sum two divisor of the form D1 plus minus D infinity and D2 plus minus D infinity with this definition now of D infinity. You will probably need to go through the point P0, I mean find curves that go through the point P0 with very high multiplicity of intersection. Okay. All right, now that we are approaching the end of this course, it will be also maybe nice to know how we are going to use Jacobians in our quest of curves with many points over rational fields. So this is the final section, so how using Jacobians for curves with many points, to find them, to construct them, or to prove that they don't exist. So, yeah, first, let's assume that we want a curve C over FQ of genus G, I can assume positive, which reaches the number of points, such that the number of its points reaches Hasvel-Serre bound. Okay. If you remember, like what we just said in the previous lecture, I mean, in order to have this, there must happen something. There must be equality in the arithmetic geometric mean inequality. And referring to the notations we had at that time, so it means that 1 over G xi, which was greater or equal to the product of the xi to the power 1 over G that was greater or equal to 1, where the xi were just integral part of 2 square root of q plus 1 plus alpha I bar. we have equality. So equality in the arithmetic geometric means inequality imposes all the xi to be equal and all the xi to be actually equal to 1. So for all I, xi is 1. And if you look at what it means that the sum of alpha I plus alpha I bar are all equal to minus 2 square root of q. But so alpha I and alpha I bar being conjugated and the product being equal to q means that alpha I and alpha I bar are roots of the degree 2 polynomial with integer coefficient Okay. But then, what does it mean? It means that I know completely my zeta function of the curve just by imposing the number of points on FQ, because it is such an extreme case, it determines completely and uniquely the zeta function of C over FQ. So obviously, the denominator is going to be 1 minus t, 1 minus qt, as usual. And the numerator is just going to be this polynomial x squared. Well, it should be the polynomial 1 plus 2 square root of xt plus qt to the power g, okay, for each of the I have here. And probably then, that's where I made a mistake. I should have also reversed it, so it's probably this also directly. Okay, so I mean, that's quite extraordinary. The zeta function is completely determined in this extreme case. You may wonder, okay, and if I'm not in the extreme case, so this is just a remark, if, how can I write that? If now the number of points on FQ is not 1 plus q plus g times the integral part of 2 square root of q, but you have a defect delta, then there is a finite list of possible zeta function for each delta, which can be actually explicitly determined for small values of delta. And if you want to know more, you can read, for instance, the book of Serre, which has been done from his lectures in Harvard in 1985. So the book is called Rational Points on Curves over Finite Fields. And you should look more precisely at the section 2.2, 2.3. Okay? And there it is explained how to do this. Now, I mean, there is one crucial thing. So if you look at Stefano Marseglia part, lectures, and more precisely at the lecture at the part 3. Here you can see that to an abelian variety over finite fields, he is able to associate a given polynomial that is called a Weil polynomial attached to an abelian variety A over FQ. And this Weil polynomial, when the abelian variety of dimension g is a polynomial of degree 2g with integer coefficients, and the roots satisfy exactly the same kind of properties as the root of the numerator of the zeta function. And of course, the coincidence is too beautiful not to be exact, meaning that what you can get is, so the theorem, which in the notes are theorem 7.4.6 for, so a Weil polynomial chi of A attached to an abelian variety. In the case of the Jacobian of a curve, chi of the Jacobian of the curve is just what is called the reciprocal polynomial. So you just have to invert the coefficients in the polynomial symmetrically. It's t to the 2g times f1 over t, where f is the numerator of zeta function of k of c. Okay, this is very, very extraordinary, because if you look at the construction that Stefano does in the course for an abelian variety, it involves what is called the Tate module. The zeta function is just given by like a power series which gather all the information on the number of points, and these two objects somehow measure the same thing. So it's very extraordinary, and well, I invite you to look at the proof, which is, I must concede, not very illuminating, but still, it gives a result. And so, something also very important is that Marseglias also says that this Well polynomial attached to an abelian variety is what is called an invariant for the isogeny class of the abelian variety. I'm not going to recall what is an isogeny. You can look at this course, to understand what is this notion. But it means that in the case where I am now, so let me focus more exactly on the case I was interested in from the beginning. So genus 5 over F47. Okay? And we wanted to know if there is a curve C over F47 such that the number of rational points is 113. And we have seen in the previous lectures that this number corresponds exactly to the case where C reaches Hasvel-Serre bound. But if it reaches Hasvel-Serre bound from what is still just above, I must have that the zeta function, or let's go directly with the Well polynomial of the Jacobian of C, must be equal to x squared, or let me write it in t squared plus integer part of 2 square root of q times t plus q to the power piece. And in that case, this value, if you want to know exactly what it is going to be 13. What is nice is that one sees that this polynomial is actually the Well polynomial of a curve, of the Jacobian of a curve. But in that case, this is equal to chi of E, where E is an elliptic curve over F47. Why can I say this? I know it because, in that case, this elliptic curve would also get the maximal number of points possible. It would reach Hasvel-Serre bound. And as I said in the previous lecture, for genus 1 curve, one knows exactly when the bound is reached. And over a finite field, which is a prime field, so Fp, here P is 47, this an elliptic curve always reaches Hasvel-Serre bound. So there is an elliptic curve that corresponds to this Well polynomial. But now it means that the characteristic, the Well polynomial of the Jacobian of C is the same as the Well polynomial associated to e to the fifth. And because of the property that I just mentioned that comes from Stefano's course, one knows that the Jacobian of C has to be isogenous to the fifth power of the elliptic curve. Okay? Just a remark before I go on with this a bit further. The remark is the following. This thing about, one has to be quite careful about this property to have or not an elliptic curve of this form. Remember that I told you that over f5 to the 7, there is no elliptic curve with which reaches Haas-Well-Serre bound. So one would like to conclude that, for instance, because of the same kind of argument I have here, so over f5, 7, it means that there is no Genus 2 curve which reaches Haas-Well-Serre bound, simply because this Weil polynomial doesn't exist, because it would have to be the square of the Weil polynomial of an elliptic curve, which doesn't exist. And this is true, but one has to be careful, because over still f5 to 7, one could have a Genus 5 curve which reaches Haas-Well-Serre bound. At least, I don't know if there is a curve, and if you look at the tables, it's not clear that it exists, but you see that the defect 0, the maximal number can't be excluded so simply. And what is sure is that there is an abelian variety over f5 to the 7th, which has exactly the Weil polynomial of a maximal elliptic curve to the 5th. So it is weird, but one has to be very careful about this correspondence between Weil numbers and Weil polynomials. So it is a bit subtle, but at least in the case where the elliptic curve exists, then I can conclude. Otherwise, one has to be a bit careful. It's just a remark here. Okay. But let me continue with this equality here, or this isogeny between the Jacobian of C and E5. So by definition of an isogeny, it means that the Jacobian of C is just a quotient of e to the 5th by a finite group. But can we do better? And in this case, we can. What Stefano does in his course is to try to develop an equivalence of category between abelian varieties, which are ordinary mostly. At least the first part that he does are for ordinary abelian varieties, and certain modules. And he does it in the case where you have like a product of abelian variety which are simples and not isogenous. So we are not in this case. Of course, this is the power of a simple abelian variety. But first, I want to tell you that as the trace here is 13, and it is not 0 in particular, this elliptic curve is ordinary. So E is ordinary. So you could simply use the equivalence of categories that Stefano used given by the linear. First, to deduce that to the Jacobian of C you can associate a certain Z module of dimension 10, which has also a property to have like an action of the Frobenius and the Feshibum. And if you put these together in the same spirit as he does for the case of non-isogenous abelian varieties, you get that to Jac C correspond a module which is going to be a Z generated by the Frobenius and Q divided by the Frobenius module of rank 5, torsion free. Okay. And what is this ring? What is F? F is going to be a root of this polynomial. So if we do the computation, if you do the computation of the discriminant of this polynomial, so the discriminant of this polynomial is going to be 13 squared minus 4 times 47. and what you get is minus 19. Meaning that this thing is just z of 1 plus square root of minus 19 over 2. And this is really nice, because you may remember that this ring is one of the imaginary quadratic order, which is principal. It has class number 1, it is principal. It is principal. So now I am left with classifying modules of rank 5, torsion-free, over a principal ring. But one knows exactly how to do this. I mean, there is only one. There is only one, and it's going to be free. So, I mean, the unique. So, thanks to that, one shows that there is a unique such module, which, if I denote, well, which is isomorphic to z of 1 plus minus square root of 19 over 2 to the fifth. Very nice. But now there is indeed an abelian variety which is going to have this module, and it is E5. E5 has the same module through the correspondence. And now what you have proved is that Jacobian of C is not only isogenous to E5, but it is isomorphic to E5. So this is quite nice because you have a description, at least, of the Jacobian in a unique way. Okay, let me stop with this for a second, and let me give you maybe an easier consequence first. So, if you look at proposition 7.4.7 and 7.4.9 in the notes, you see that, and I have already used it for E5s, chi of A times B is k of I times k of B. But mostly, I mean, all the properties that I have here, they are just deduced by linear algebra because the Weyl polynomial is so nicely defined as a determinant of a certain endomorphism. And if phi between A and B has finite kernel, then chi of I divide k of B. In particular, if C to D is a non-constant morphism between two curves, and the genus of D is positive, just not to say something that would be trivial, then the characteristic, the Weyl polynomial of D, of the Jacobian of D, is going to divide the Weyl polynomial of the Jacobian of C. But this is super nice because, as a corollary, if C reaches Haas-Weyl-Serre bound, then, with the notation just here, D reaches Haas-Weyl-Serre bound. Quite nice, right? I mean, simply because in that case, the Weyl polynomial of the Jacobian of C is just going to be, as we have seen, the product of a certain power, a power of a certain polynomial of degree 2. This must be the same power of a polynomial of degree 2, and then it must reach exactly Haas-Weyl-Serre bound for the same reason. As an example, remember that we introduced last time the Hermitian curve in an exercise. So H, that was x to the q plus 1, at least the affine equation yq plus y over fq square. And we proved that H reaches Hasse-Weil-Serre bound. So any quotient of H is also going to be a nice curve. And how do I define a quotient? I mean, it's simple. I take S, any numbers that would define Q plus 1, and I take H prime, the curve x to the S, or yq plus y. And the morphism between H and H prime is obviously to xy. I'm going to map it to x to the power q minus 1 over s y. Q plus 1 over s y. Okay, so this curve, you see, I mean, I had a way to populate my tables, but for very rare genuses. But now, I mean, doing this, I can also and this is going to be a curve of genus a bit less over the same field. So when I have this curve, I can also populate some other genus which are lower. Not all of them, of course, that would be too beautiful, but at least I can have more examples. Okay. So to conclude, let me come back to what is my main goal, so genus 5 over 4, F47, 130 points, and from this we already deduce that if such a curve exists, then the Jacobian of C must be isomorphic to E to the fifth. This way of proceeding is part of what Serre himself introduced for the genus 2 case. I mean, this philosophy is the following. You're looking, here you have curves. You have the world of curves over your field FQ. And you don't know if an object that would have the curve with many, many points exists or not. So you send the problem using the Jacobian of C to a bigger box, which are all abelian varieties over FQ of dimension G. All right? And what you have is that inside this big set, you have the abelian varieties that would have like the right Weil polynomial, as we have seen. I mean, so this would be the abelian variety with the right Weil polynomial. So as I said, if we are in the case of we reach the Hasse-Weil-Serre bounds, then there is only one Weil polynomial possible, otherwise there would be several to test. So you have all of them. And the question is, here you have the curve. So let me do it by a blue point. Are some of these points that I have here inside the locus of the Jacobian? So do some of these points come from a Jacobian? So in my particular case that I have here of genus 5, so it would be like I take the point e to the fifth, so apparently I should have only one because I'm looking at only one, but here that's the subtlety. I mean, the Jacobian doesn't come as just the abelian variety, but it comes with a principal polarization. So actually I should differentiate abelian varieties now, and I'm going to speak about polarized. Oh, maybe that's not visible. So polarized abelian variety up to isomorphisms. So now I'm adding to each of them a polarization. And so on, okay? Because the Jacobian comes with a polarization. And I want to know if one of these points now is inside the locus. And one thing about the Jacobian, if you watch, for instance, the the course of anastomosa is that this polarization A is not any polarization, it is a principal polarization. So you want that these objects also, these polarizations on these objects are also principal polarization. Is it always possible? No. There are some abelian variety and classes of isogenies of abelian variety which don't accept principal polarization, so sometimes you can exclude them just like this. But now, I mean, of course, on E5, I mean, if you know a bit about polarizations, there is always a trivial polarization, which is just what is called the product polarization. But one nice thing is that the principal polarization on a Jacobian is what is called also undecomposable. So I still need one more color. So it's an undecomposable principal polarization. Okay? And now the question is, among these polarizations here, is there one that would be undecomposable? So let's assume, so let's say that, I mean, A1 is a product polarization, so this one is not going to be the good one, but here we have a nice principal polarization, A2, which is indecomposable. This now, the Jacobian of a curve. Can I say, okay, I mean, I put enough hypotheses now, I win. If the genus would be 2, then I would say yes. Now you have done, you can relax, you found the right abelian variety. I mean, this is going to be the Jacobian of a curve. This works only for genus 2. For genus 3, it is almost the case, but still, I mean, one doesn't know, and this is the reason why I explained last time that if Serre found a formula for the number of points for any genus, maximal number of points of any genus 2 curve, the genus 3 case is still open. So it's not enough. And when genus 4 and 5 comes, I mean, it's even worse, because even geometrically, you can have something which is principally polarized with a polarization which is undecomposable, which is not the Jacobian of the curve. So even over the complex, finding where the Jacobian of the curve lives among abelian variety with principal polarization is already a big problem, which is called the Schottky problem. Okay, for which, I mean, there are solutions, but all of them are not directly applicable over a finite field. And to conclude, I mean, what you would need to do, I mean, to solve this problem, is to find a way to maybe express the Schottky problem over a finite field. And there are ways to do this using the theory of theta functions that Anna Somoza also explained to you. You can find some expressions in thetas. Of course, theta live over C, but you can have like analogs that lives over finite fields. And using the solution of Schottky problems that exist over C, you could maybe find conditions over finite fields as well to see if you live or not in the locus of the Jacobian. If you don't, perfect, then I mean there is no solution to the problem. If you do, then it means even more work. Yeah. And so this is the conclusion. We reached exactly the point where we wanted, meaning that we have studied as much as possible this problem of the genus 5 curves over F47, seeing how what is done over the complex with theta functions can be useful, and the equivalence of categories that also Stefano Marseglia introduced in his course was also useful to try to understand, have like an explicit expression, at least I explained it for the abelian variety, but you can also have it for the polarization. Thanks a lot, and well, I hope you enjoyed the full course.